Hi everybody, welcome back to class. We've only got about 8 or 10 minutes left here today, so I'm going to try to give you just a quick introduction to static friction, which is a really cool topic that is involved in our everyday lives. For example, if you try walking somewhere, guess what? You use friction. So you use this every time you take a step. Once you get out of bed, you're using friction in one way or another. I have friction between my shoe and the ground, which we talked about using Newton's third law. If you remember the action, reaction, force pairs. I push on the ground pushes back on me. So if I didn't have any friction, I'll be walking and I'm not going anywhere because my feet are just sliding, which is not very great. One place you also experience that in everyday life is ice. So I know we don't have a lot of ice in California, but if you go to the mountains, you get ice. If you go up north, you get ice. So there's plenty of ice out there in the United States and the rest of the world. So and if you have no friction, again, because ice is very, very low coefficient of friction. We'll talk about coefficients in a few minutes. If you got not enough friction, you are going to perhaps slip and fall, which is not much fun, and you kind of learn the hard way, I guess, as older folks have probably experienced once or twice. One comment I want to make before we go ahead, we're mostly going to talk about static friction today, which is where you're not sliding. There's also kinetic friction where you are sliding, and so it's actually easier to deal with, so we'll deal with that second. But in general, friction applies to not just objects. Like I've got a box here. Let me use that. Okay. Some boxes on top of a table here. It applies not just to objects together, but it also applies to any kind of fluid or which includes liquids and gases, if you remember. I mentioned that before. So for gases, you can think of like air resistance in a car. You get lots of air resistance driving quickly in a car. For liquids, imagine I drop a rock through some water, it slows down, right? So you can have some kind of friction pushing backwards. We often just call those drag forces. Okay, well, let me jump ahead here. I took the liberty to actually write a couple things on the board just to save some time. Friction forces, just a couple general statements. One, they always act, or the friction always acts in a direction to oppose motion. So if I push this way on my box here, the friction force will be back. If I drop my rock in the ground, in the liquid, friction will be going backwards. So it's always going to oppose motion. That applies either static or kinetic. If it's sliding, the friction will still be going backwards. Okay. The second important general property of friction is it depends on the surfaces involved. So here I've got cardboard on wood. That's got a certain coefficient of friction. I'd have to measure it experimentally to get the exact number. One typical one would be your shoe on cement. Maybe you're walking down the street. So it'd be rubber on cement, perhaps. That'd probably be similar to a car tire on cement. That's going to be about 0.8, I think, typically. Again, I always rely on experimental values. Now, if it's wet, then you get less friction, right? You're going to slide more easily, you get less traction, we call it. So the coefficient of friction goes down a little bit. You probably have 0.6 for a wet shoe on cement. Some things have very low friction, like your elbow, your joints in your body, your knees, or whatever. That gets down to like 0.1 or less. So a pretty small number. You don't want a lot of friction in your joints in your body. Other low friction things would be anything with lubrication. So like you get some Teflon, you get some ball bearings. You want to get that number as small as possible, so you can get very low friction situations. So the materials involved matter. And there's a chart of different common materials that we can look up. Number 3, it depends really on how hard you squeeze the materials or the surfaces together. This right here, this cardboard box is being kind of squeezed down because I put a big weight on it. This book weighs a lot, so it's getting squeezed down. It's caused by the force of gravity. That's a pretty common one. Like if I push a refrigerator, it's being pushed down by gravity. Mg is coming down. Creates a normal force going back up. This is equilibrium, so I have mg going down, normal force going up, right? And we looked at this before a couple chapters ago. You know that usually the normal force simply equals mg. As long as you're on a flat surface, you don't have acceleration. On an inclined plane, it gets a little trickier. We'll get to that when we get to that. But often just the normal force is the mg. That's how hard it's being squeezed together. Let me show you a cool example, though, of squeezing. And I'm looking at my time. I've only got 5 minutes of class left, guys, so let me try to go faster. I've got a book here. I'm holding it next to the wall. I'm holding it upwards with my hand, mostly pushing upward because it wants to fall. It's a heavy book. What are the force sections in this book, guys? What force is? Let me hear what force is. All right, mg, right? I always say for a force diagram, mg should be the first one you put in there. The weight. If you're on Earth and with gravity, that's probably a good guess. Easy one. Also, yep, normal force. Yep, pushing out from the wall because it's touching the wall, so it should be normal force. And any other forces? Yep, you got it. Friction. Friction is pushing up. It's only touching a little bit, so there's not much friction. I hear it sliding though, so there must be a little friction. Now, a trick thing I can do here is push really hard. Pushing really hard. It wants to fall down because it's pretty heavy. I got to push really hard. This is about 10 pounds. And I'm pushing hard enough, squeezing it enough to make the friction force big enough to balance the downward mg, the gravity pull. So that's pretty neat. And so we can think about that in many ways, but basically it depends really on how hard you squeeze the objects together. All right, let me do another example. I've only got 4 minutes left. Let's look at a box on a table, which I happen to have right here. How convenient. If I push a little bit, it doesn't go anywhere. Wow. So I can draw a picture of that. And I always recommend drawing pictures in general of any situation you're dealing with. And I would have drawn the vertical one, except I'm a little low on time here. So force, I'll put force hand, pushing to the right, and acceleration 0, right? So it's in equilibrium, which means the net force is 0, right? Remember that from Newton's second law. You guys got that? Yeah. So my force hand goes that way. I'm going to call this F static. There's some friction force opposing it. If I use 2 fingers, twice as hard I'm pushing. It still goes nowhere. So I push harder. The friction force got bigger. So friction force is kind of weird. It changes depending on how hard you're pushing. So static friction is kind of a weird animal. I push a little harder. Let me try. I'm guessing it's going to go nowhere. I'm going to try 3 fingers. I'll just guess. That's my prediction. It still didn't go anywhere. Okay. I really am pushing harder. I promise you. But I know there's some amount I can push. My whole hand started to move. Okay. So there's some amount. It gets bigger, 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 and then eventually it starts to move. So the cool thing is to look at a graph. It's graphing. Force friction and force hand. Or I can do push or hand. Again, I pushed a little, friction was a little more, a little more, a little more, a little more. And if I graph that, it's going to be a straight line. It goes up, up, up to a max, and then it's going to come down. That's going to be my kinetic regime. That's sliding friction. This is my static. And there's some value here. That's my Fs max. I'm so out of time. I gotta let you guys get to your next class. So give me just a second to show you the formula. Kinetic is usually gonna be smaller than the static max. It's just once you get, like if you try pushing a fridge or something, once you get it going, it's easier to keep pushing. Let me give you the formula, and then we'll pick up right here next class. We left off. Fs max. The biggest it can get is gonna be a mu, my coefficient of friction, times our normal force. And the general expression, because it's weird, it changes, is Fs equals or less than equal to us times n. So again, that normal force is really determining how hard you're squeezing them together. The coefficient of friction is our mu sub s. Mu sub k, it turns out, will be the kinetic coefficient will be a little bit less than mu sub s. And you guys have got to get to class. So I'm going to let you go. So study this. Read ahead in the book, please, and feel free to ask me any questions by email. And I will talk to you soon. Have a great day, guys. Bye-bye.